Hello and welcome to your journey in multivariable calculus. In this very first video, we're going to introduce the notion of multivariable functions. So up until now, we have likely seen functions that have one input variable and one output variable. So you may have seen situations where y is a function of x. Or whatever variable names we choose. So this just means that in order to predict the value of y, I need to know the value of x. And in functions of two variables, which you would probably argue that this is an example, we define functions of two variables to be any functions in which there are two input variables. So in this notation here, for instance, we have one output variable called c, and that output is going to be a function of two input variables, one being called capital I and one being called lowercase p. To give this some context, suppose you're a beef producer and you want to know how much beef people will buy. This depends on how much money people have and on the price of beef. The consumption of beef, so that's what C is, which is measured in pounds per week per household. So in other words, how many pounds does a household buy on any given week, is a function of the household income. So this is going to be measured in thousands of dollars per year. So a family probably earning $100,000 a year is going to be able to consume more beef than a family earning, say, $30,000 a year. The consumption also depends on the price of beef, because even though you may have a steady income, if the price is really high, you might wait until it's on sale to purchase it. So the amount consumed on a weekly basis is a function of the family's income, annual income, and the price of beef measured in dollars per pound. So here we kind of have a table of averages. So not every family will adhere to exactly these numbers, but these are some kinds of averages. Values of P are shown across the top. So we have four different prices: $3 a pound, $3.50 a pound, $4 a pound, $4.50 a pound. Values of I are on the left side: $20,000 a year, $40,000 a year, $60,000, $80,000, and $100,000 a year. And inside the corresponding values are the f of I comma p. Another name for that is C. So for instance, a family that makes $40,000 per year, when the price of beef is $3.50 per pound, we find where that income intersects with that price. And so we could say that that family is expected to purchase about 4 pounds of beef per week. There's another example. If a family makes $100,000 and the price of beef is $4.50, then I would expect that family to purchase about 5.5 pounds per week. So one of the other things that we can do in this table is we can say, well, I want to see how a family earning $20,000 per year behaves as the price of beef goes up. So if I just focus my attention to this one row, then what that allows me to do is to see that as the price of beef increases, I see that the amount consumed by that family decreases. The same goes for a family earning $40,000 a year. I can see that when the price of beef is $3 a pound, they consume 4.14 pounds of beef per week, a little bit less as the price goes up 50 cents per pound, less even as the price goes up by another 50 cents, and they consume the least when the price of beef is the highest. So with that said, we can also look down a column. For instance, I may want to see how families behave or how their consumption changes when the price of beef is fixed at $3 per pound, but I want to see the relationship between income and consumption. So what do I see here? As income goes up, the consumption is also increasing. We can see going from about 2.7 pounds to 4.1 to 5.1 to 5.4, 5.8 pounds. We see that the consumption goes up as income goes up. And in fact, we could isolate any group. We could say, well, what about when the price is $3.50? Well, for all comparisons between $3 a pound and $3.50 a pound, the families purchase less, but we still see the trend that as the price goes, as family income goes up, the amount of consumption goes up as well. So we can now answer some questions about this table now that we have a sense of how it works. Using some of the function notation, we recall that C is the output that we get when we input the family's income and the price of beef. So here we can say that when, and we can say that this equals, well, I have to look at the family that makes $80,000 a year, and at $3.50 a pound, that's going to be this value here, 5.29. And so we could say a family earning $80K per year when the price of beef is $3.50 per pound, is expected to consume 5.29 pounds per week. We don't need to say per household because we're already talking about this one specific household. Now we can say the same thing here. Notice that our notation is a little bit different. We're not using F of, but we're using C of. And that's totally fine because sometimes when we write even things in algebra, like if we said C is F of T, then a lot of times you'll see the function just show up as C of T equals and then whatever that function is. So this notation is no different, just so you're familiar with the different ways you might see function notation in a multivariable calculus class. So here we have a family earning $40,000. Price of beef is $4.50. So that would tell me that I would expect that family to consume 3.88 pounds of beef per week. We can also ask questions about for what pairs of income and price is the consumption 5.6 pounds per week. So if I look in this table and I look for 5.6, I see that, there it is. So 5.6 is the amount of beef consumed for a family earning $100,000 per year when the price of beef is $4 per pound. So I could say that for this particular case, F of 100, $4, that leads to a consumption of 5.6 pounds per week per household. So one of the things that we often want to do in multivariable calculus is, because this is a three-dimensional relationship, we have two inputs and one output. Notably, in our context, we have I, the income, and the price of beef, and both of these are factors that lead me to determine the total consumption. So I have a three-variable problem here, and in order to be able to think about this, I would need three axes. So imagine that this is kind of the floor, if you will, and that we now have also a height to that room. We don't just have length and width, but now we also have a height, and we can arbitrarily label the two input axes I and P, and then the output axis would be the amount of consumption. So we'll get at how we plot points in here, but if I wanted to plot, for example, 104, 5.6, I would need to come over here to see where that income is 100, and we'll just set that right here. So we'll say that's 100, and then for a price of $4, so I can write 1, 2, 3, 4. So this is $4 a pound. The third component that I would need is the 5.6, so 1, 2, 3, 4, 5, 6. Now the thing is, the hard part about plotting in three dimensions is perspective, because as we're over here, that point is not going to quite go up this high to 5.6. it's only going to go up that same distance, but located where these two points intersect. So if I draw this line across here, and then I draw this line down, this right here where these two points intersect, that's where the input of 100 meets the input of 4, and now from there I need to go up about 5.6 units, which is that length right there. So that length will lead me to the location of this point right there. So this is the point 100, 4, 5.6. So we just need a third dimension. If we only had two variables, I and p, then we would basically just plot one ordered pair in this two-dimensional plane. But with the third variable, I need a third dimension in order to be able to look at that. What we often want to do is reduce the problem from a three-dimensional problem to a two-dimensional problem for a number of reasons. The most primary being that it's easier to think about. So if I look at this notation here, what I notice is that I is a variable and the value of p has been fixed at $3 per pound. So what this means is this is going to be price fixed at $3 per pound. And so that means that the two quantities that I have that are still variables are I and C. So I have an input of income and I have an output of consumption. So if I wanted to take a look at the relationship here, I would be comparing the income and the corresponding consumption, but this graph would specifically look at when P is fixed at $3. So this graph that I would see here would only be for P equals 3. In my table, what that means is that I'm looking at just the incomes of 20, 40, 60, 80, 100, and then the corresponding consumptions under $3 per pound. So here my labels would be 20, 40, 60, 80, 100. And along here, for instance, I would plot the point 20, 2.65. So 20,000 would be here. 2.65 would be somewhere here. And so that would correspond to the amount of consumption being 2.65 pounds per week for a family earning $20,000 when the price of beef is fixed at $3 per pound. Now, of course, I'd have all the other ordered pairs. I'm not going to produce that in this particular graph. But I've created a two-dimensional problem out of a three-dimensional problem by fixing one of the variables, holding them constant. No different is in terms of what we have here. Here we're saying that the income is going to be fixed at families earning $60,000 per year. And so once again, in that context, what that would mean is the remaining variables that are not being held constant are price as the input and consumption as the output. So the prices we know varied everywhere from, I'm just going to create a little break in the graph here, and we'll start at 3, 350, 4, 450. And so now I could go ahead and say that this is only for when I is equal to 60, and I could produce the graph of the ordered pairs for price versus consumption. So remember, when we set I equal to 60, we're now focused in on these values and these values. So for $3 a pound, I would plot 5.11 as the consumption. So 1, 2, 3, 4, 5, 6. 5.11 would be right about there. So this would be the point 3, 5.11. So I could say again that if the price of beef is $3 per pound, then the consumption will be 5.11 pounds per week, but only for families earning $60,000. So these two notations here, now notice that I am claiming that I'm going to be holding I constant, but I haven't specified what value of I I'm going to be looking at. In terms of our table, what we should be thinking about here is we're going to be looking at the relationship between price and consumption, because again, I'm holding I constant. This is going to be my constant right there. So on this graph, what I could do is I could actually plot multiple curves, and I'm just going to kind of create some sketches here, and these could all be for different incomes. Like maybe this is for income equals 20, this line is for income equals 40, or income equals 60, and so on. I would be looking at basically perhaps different values of I. In this final example, we have again cost as a function of these two inputs, but if I hold P constant, that means I want to look at the relationship between income and consumption, maybe for different, I'm just going to draw something a little bit different here. This is going to be for different price points. P equals 3, P equals 3.5, and so on. And so by holding P constant, that is just a statement saying, I only want to look at the relationship between the two things that are not being held constant. But the first two problems are really just specific values of holding income and holding price and income constant. These are kind of just saying that we could be holding I constant at whatever value we want, but the point is that the relationship that we're focused on studying is that between the remaining input variable not being held constant and the output variable. So here are those actual graphs, and so we're looking at two-dimensional graphs of three-dimensional data. Once again, we have three-dimensional data because we have price and income as inputs and consumption as the output. The symbols we use to denote two-dimensional space is what people would call R squared. This kind of bolded, this scripted R, this is what we use to represent the real number system. And if you were to write that out by hand, normally you would write the capital R with a double little leg here, and that means real number system. This is the set of all real numbers in mathematics. Remember, all real numbers that could be fractions, decimals, zero, positives, negatives, irrational numbers like pi is a real number, anything that just does not have an imaginary number in it like I. So in this graph here, what we are actually looking at is problem number, or letter 2. We're holding, let's see, we are holding the income constant. So what we're looking at is letter C. So here we are holding income constant. And the reason we know that is because the two axes are the variable axes. This is the price axis. This is the consumption axis. And so we just have one graph or one function per income. So here we clearly see that actually it's pretty interesting that for all of the 5 different income groups, as the price of beef rises from $3 a pound to $4.50 a pound, consumption goes down. Now, not all in the same ways. But they do look fairly parallel for the most part. Of course, there are going to be some differences. But we see that there's a huge jump in consumption from $20,000 to $40,000 a year. But then $80,000 incomes to $100,000 incomes, their consumption curve does not rise by as much. So we see a lot of interesting features here, things that we can describe. But we do see that as P goes up, as P increases, consumption decreases for all I. In the next graph, we could also look at holding P constant. And the reason I know I'm looking at that is because here I have I versus C, income versus consumption. So we notice that these are all very, very close together, very little difference across the 4 different price groups. But what I do see is that from 20,000 to 40,000, there's a pretty big jump in consumption, still a pretty big jump for 40,000 to 60,000, not quite as large. And then we see very little change from the 60 to 80,000, and a little bit of a bigger change from the 80,000 to the 100,000 group. But again, we're taking a look at three-dimensional graphs in two-dimensional space. And this is often what we want to do with higher dimensional problems. When we do get into problems that involve 3, 4, 5, and upwards of that number of variables, then we want to try to reduce the problem to make it visualizable in some form or sense of our knowledge. So it's no different than any engineering application where we want to try to take a complex problem and make it as simple as possible. To wrap up our introduction to multivariable functions, let's start thinking in three-dimensional space, R3. Now, some people call this R cubed. I like to call this R3. R3. Okay, so we have the coordinate axes in three-dimensional space. It's pretty arbitrary which axis is x and which one is y, but the z-axis is typically the vertical one. So think about z as being the output when you input two variables, x and y. So now y is not your output, it's not your dependent variable anymore. X and y are both inputs, and both x and y lead us to determining the value of this third variable z. So this is one common way to draw this x-axis here, y-axis here. We now have not 4 quadrants, but we have 8 octants. And that may seem rather confusing at first. What do you mean by octants? Well, octants means 8. And if you think about this as being an octant, that is, you kind of have this, almost this cubical shape, then you have 8 of these. 1 here, 1 here, 1 here, 1 here, and then 4 more, but underneath, down in the negative z's down here. So when we locate a point, as we've mentioned, the first thing we do is we locate the first coordinate. So if this is the x-axis, which by the way, these tick marks, I'm drawing parallel to this axis here. And the tick marks on the y-axis, I'm drawing parallel to the x-axis. So I see that I need to, along the x value, move 1 away from the origin. Now I need to walk 2 units in the y direction. So 1, whoops, I'll write this as 1, 2. And so we see that that point leads me to the point 1, 2. This is now in the xy plane. So this point right here that I'm going to draw in blue, if I drew that point, that's a point in the xy plane. We have 3 planes. We have the xy plane, then we have the yz plane, and then we have the xz plane as well, which is kind of this wall right here formed between the x and the z axes. And so then, of course, we're going to go up 3 units. So 1, 2, 3 means we go up 1, 2, 3 in this direction. Again, the perspective makes the perspective kind of makes the 3 here appear lower than the actual 3 value here, but notice that it's closer towards us perspective-wise. And here we can see that the point 0, 0, negative 1 would mean you don't move any units in the x direction from the origin, no units in the y direction, and then just down 1 unit. So it's basically on the z-axis, but it's down 1 unit below the xy plane. Okay, so the origin, well, I mentioned the word origin. When we say origin in R3, the origin is not the point 0, 0 like it is in 2 dimensions, but it's the point where all coordinates have a 0 distance. So this point here is the origin. So let's get to thinking about these dimensions. You are 2 units below the xy plane and in the yz plane. What are your coordinates? So let me draw these 3 axes here. This is x, this is y, and this is z. So let me point out once again that I've mentioned it verbally that this right here, and also extending back into this region, that whole sheet of paper is considered the XZ plane. This is the XZ. This plane here, which runs from left to right, and it continues going in this direction infinitely as well, that is called the YZ plane, because that's where we're in a our x value is 0, but our y and z are somewhere within that region. So it could be this point, or this point, or this point, or this point. And then down here, to complete our room, you could kind of think about this as the floor. And the floor represents your, you guessed it, xy plane. So that, now that we're a little more oriented, we can kind of think about what this is saying. We've got our x, y, and z axis. You're 2 units below the xy plane. So we're 2 units below this sheet of paper. So if this axis kind of continues going down, we're 2 units below the ground level, and we're in the YZ plane. Well, wait a minute, to be in the YZ plane, that means we're smashed against this north wall here. So we know that inside of the YZ plane, the x value has to be 0. To complete this picture, in the xy plane, your z value has to be 0. And to be in the xz plane, your y value has to be 0. We're not moving left or right at all. So if we're in the xz plane, or sorry, in the yz plane, that means we're somewhere in along this wall. Right? This wall kind of goes, imagine this to be the portion of the wall below the ground. We're somewhere in that plane. So what do we know about that plane? Well, we know we're 2 units below it, so that means our z-coordinate is -2. And because we're in the yz plane, that means our x value is 0, and we're not really given any information about the y value. That y value could be here, or it could be here, or it could be over here somewhere. As long as it's, whoops, can't be there, it has to be 2 units below, so it could be there, it could be there, it could be there. So the y value can be anything we want it to be. So we'll just say any point of the form 0, y, -2. You are standing at the point 452, looking at the point 0.503. Are you looking up or down? Well, to really highlight this fact, all we need to look at is the z value. Because if I'm looking from a lower z value to a higher z value, that means I have to be looking up. I encourage you to begin sketching these things as well as you can, so you first of all get the geometric three-dimensional space plotting component down, but just so you get a better sense of visualizing and how 3 dimensions work. So here's one point. We're at x value 4, y value is 5, 1, 2, 3, 4, 5. So our point is going to be somewhere here in the xy plane, but then up 2 units. So we'll say up 2 units is 1, 2, that's going to be about there. I'll just draw a little dotted line. Now looking at the point 0.503, so that means I go half a unit this way. So I go half a unit this way, and then I go 3 units this way. So that's going to lead me to this point here. But then that point is elevated 3 units off. So 3 units off will be a higher distance than 2 units off. And so 1, 2, 3 will put me about there perspective-wise. And so in order to be looking from this point to this point over here, I'm going to be looking up because it's higher off the ground. So we are going to be looking up. Okay, so 12.3 above. Here is this point located at 1, 2, 3. How could we find the distance between this point and the origin? Recall Pythagorean theorem is c squared equals a squared plus b squared. That allows you to find the length of a right triangle's missing side given the length of 2 other sides. So let me go ahead and copy this little graph here. And so what I need to think about is, first of all, I want to measure the distance between this point and this point up here. So if I draw a line across from this point, connecting this point, I want to know how long that line is. But the thing that I have to keep in mind is that this is kind of, it looks like a right triangle if this point right here were on the y-axis, but it's not. So I have to remember that there's actually, and I'll draw this in a different color, there's actually a right triangle here between those points and these 2 points. And that right triangle here, I could actually draw a right angle there. And the reason I can do that is because this line here is inside of the xy plane. And this line here is perpendicular to the xy plane. It's coming directly straight up from there. And so because the z-axis, all 3 of these axes are perpendicular to each other, these 2 lines have to be perpendicular to each other. So in order to calculate this, I would have to think about what this A, what this B, and what this C are. So the first thing I should note is that C squared is going to equal A squared plus B squared. And I already know the value of B. That's just the distance from the xy plane up to that point. So B is going to be equal to 3. So far I have C squared equals A squared plus 3 squared. But my problem is that I have 2 unknowns remaining. I want to solve for C. I know that's going to be the square root of A squared plus 3 squared. But I don't know A. The one thing that I do know about A is that I can actually form a right triangle inside of the xy plane. And the way I'll do that is by looking at this portion here. And this A is really the hypotenuse of this right triangle right here. And the reason I know that that's perpendicular is because this line, this distance here, which I know is 1, and this distance here, which I know is 2, this is just the distance from the origin to the x location. And this distance here is the distance from the origin to the y location. So I know that that's 1, I know that that's 2. So to resolve A is going to be, or A squared is going to equal 1 squared plus 2 squared. Which means A is going to be the square root of 1 squared plus 2 squared. Now for a second, so that we can generalize our findings to any point and finding its distance, what I'm going to do here is I'm just going to write C is equal to the square root of, and then inside of here I'm going to replace A with 1 squared, or the square root of 1 squared plus 2 squared, and that quantity A is getting squared. So I have to put a square on top there, plus my 3 squared. You notice I haven't actually written 9, or I haven't actually combined terms. And the reason, again, I'm doing this is because I just want to see how this would be done for any point, not just this one point. So if I square a square root, what I will have is the square root of 1 squared plus 2 squared plus 3 squared. And one thing that we should notice here is that the distance from the origin of any point, x, y, z, distance of any point from origin of the form x, comma, y, comma, z, the distance of that point is going to be the square root of the components, sum of the components squared. So it didn't really, the fact that the components were 1, 2, and 3 were really not significant. They just helped us set up our drawing. But in general, this is the distance of any point from its origin. So it's just an extension of Pythagorean theorem. We just had to use Pythagorean theorem twice in order to do that. So just keep in mind that this is from the origin. If it's the distance between 2 points, you got to think a little more carefully about that. Okay, so now that we have some of these tools under our belt, let's now look at the 2-dimensional graph of consumption of beef as a 3-dimensional plot. So what I'm trying to convey here is that if I wanted to look at consumption versus price, and I apologize, a lot of 3D software does not put things where you want them. So actually this is the p-axis here, and the value of p is increasing as we move away from the origin. So this is, if we look at this graph, if income is fixed at 20, then the price of beef versus the consumption, I could also label this axis consumption here and call this 3, 3.5, 4, 4.5, 5, and 5.5 as the different consumption values. Then I can see here in this, if I kind of imagine that this is really a two-dimensional graph, just kind of going the opposite direction than we would normally draw it, that basically what I see here is that as the price increases from 3 to 3.5, 3.5 to 4, 4 to 4.5, I see that my points are dropping lower and lower, because as price goes up, for a family earning 20,000, we know that the consumption went down. Now if we scooch back this way, we go from 20,000 to 40,000, so here is 40,000, and that's us looking at, draw this in a different color here, there's the 40,000 point, and now we're looking at that two-dimensional graph. That's going to be these points that, again, as price goes from 3 to 450, the consumption is going down. So these two sets of ordered pairs here are really just these two lines here that we're seeing, decreasing, decreasing. That represents these 4 points and these 4 points. So once again, we could increase our consumption to a different, or our income to a different level, specifically 60,000. And at 60,000, I can again compare those points and look at the consumptions. And those consumptions are here, 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 and here. Those are, again, going down. I could do the same thing for 80 and 100, but the difference now is that I've created one pair of PC axes for every individual value of I, and I've kind of staggered them apart like this to give it the perspective that they're three-dimensional. So it's kind of like we're unfolding, almost like one of those lightsabers you might have had as a kid where you could kind of slice it forward, and then all of those barrels would kind of come out, and it would form this sword-looking thing, and then when you pushed the tip back in, it sort of telescoped it back in. Or think of a telescope. It's like we're telescoping these points out. Now the same graph, if we rotate it, we can also see that if we looked at I versus C, so looking at it this way, that I could actually see that these 1, 2, 3, 4, 5 points, these points here, actually form what we're seeing when we look at income versus consumption, which is this graph here. As income goes up, consumption goes up, like according to this almost cubic looking function, and that's what we're seeing here. Again, just where our perspective is looking at the I and the C axes individually. So it's probably a little bit easier if I just rotate that whole graph. And if I rotate this graph here, I can actually see, oh, I'm sorry, this is really kind of the income versus C graph here. And this one I'm looking at P versus C, and those are my lines that I saw that are just staggered, set apart by this third dimension here. So when we look at functions, a graph of the function will sort of form what we call a surface. And a graph is the set of all points that satisfy the function z equals fxy. So for instance, if you created a wireframe here, if you kind of laid a flat sheet of paper down on top of these 4 points, and then you created a new sheet for these 4 points, and then for these guys, and then for these guys, you could kind of see how if I tossed a blanket over these points that were just suspended in space, I would get something that would look like kind of like a fun looking water slide with a bump right here. And hopefully you can kind of see that if we connected those points, we would get a nice three-dimensional This is the way I kind of view it as a slide. Going this way, you created a bunch of little wireframes in here, and then even smoothed it over, you would get a smooth-looking three-dimensional function. So we now have said that the function is, normally we're going to be given an equation for this. Here we were just given the ordered triple, so we were looking at just the data points. But a graph is the set of all such points. So if you have an actual equation dictating the function, then the collection of all those points smoothed over will form the graph of it. Okay, so here we have three functions, and at first sight they may just look like individual values for x, y, and z. Now z equals 3, this function here, z equals 3 is going to be a graph, and it's going to be the graph of all points that satisfy this equation. So what's the set of all points that satisfy the equation z equals 3? Well, this function says that this is going to be the set of all points. Set of all points where z equals 3. Okay, well that could be any point of the form x, y, 3. So it doesn't matter what the values of x and y are, just as long as the z value is 3. Well, in this graph here, I see that, okay, for any value of x and y, as long as I'm on that blue sheet, I'm good, but I see that the height varies, right? The z value isn't 3 everywhere. The z value there is looks to be more about 4. The z value here looks to be more about, or whatever that value is, looks to be about that value there. So the z value is not always 3 on this surface. If I look at the next one, I also see that this thing is called a plane. The points on this plane are allowed to be at different values of z. But this one here, I see that as I vary the value of x and y, I see that my z value is always the same, that if I walk along this blue sheet of paper, my z value is not going to change at all. So this graph here is the set of all points where z equals 3. For instance, this corner point, which is going to be that value of x, that value of y, that value of z, I can't really read my own tick marks here. 1, 2, 3, 4, 5, 6, 7. That looks like it's the point 7, 1, 2, 3, 4, 5, 6, 7, 3. And every single point along here will be something, something, 3. That point right there will be, let's see, x will be negative 7, y will be positive 7, and z will be 3. So in a similar fashion, if we look at y equals 3, that's going to be the set of all points where the y value is 3, and the x and the z can be whatever they want because that equation doesn't say anything about x and z. So I just have to make sure that my y value is always 3. In this graph, I actually see that this plane forces 1, 2, 3. That forces y to be fixed at 3, but the x value, I can move forward and backward, I can move up and down on this plane, but I can't move left and right because this blue sheet of paper limits me to a y value of 3. And similarly, for x equals 3, that's going to be the set of all points where x is 3. Doesn't say anything about y or z, so those are allowed to vary. And by default, that has to be this one. But I also see 1, 2, 3. I see that all the points on this plane are located at an x value of 3. So this graph must be x equals 3. As we begin thinking more about multivariable functions, we'll start to look at more complex graphs, but these ideas here are so critical in helping us visualize. So always take the time to stop and plot.